Oh, okay. So the urea cycle, in the urea cycle, basically nitrogen is going to be transaminated. And how's your morning going, by the way? Like good, huh?
Quite good. Sorry. It's going good. I was making breakfast for my son.
How's that horrible chemistry teacher treating you?
Oh my goodness. He's fine with this. What's his favorite cake, by the way?
Oh, what is that guy's favorite cake? Oh, I don't know. I don't know. Let's
see. That's a great question, honestly.
It is a beautiful question. You know, there's something, I think there's something in that syllabus that I can look at that'll probably give me a little bit of a hint.
Okay.
Okay. So, if you kind of take a look at this, we have, this is kind of wrong in the book. Okay, so in the mitochondria, we have CO2. CO2 is going to be utilized to sit there and make, it's going to take the ammonia and make the ammonia to ammonium. So you're going to be doing some transfer of that hydrogen ion from, and then it's going to take that ammonium and then it's going to attach it to the carbonyl phosphate. So then the carbonyl phosphate, it's going to actually go through, it's going to lose the phosphate to make inorganic phosphate. And then we're going to end up with L-citrulline. So then the L-citrulline is going to go through the cycle, continue going through the cycle. You're going to get from L-citrulline, you're going to use ATP. That ATP is going to be these two organic phosphates, or it's going to lose organic phosphate. It's going to lose diphosphate. And then you're going to end up with AMP. You're going to come in, your amino acid is going to react with the L-citrulline, and then it's going to end up making the amino acid aspartate. It's going to end up making arginosuccinate. And then the arginosuccinate is going to be converted to fumarate by another enzyme. And then you're going to get L-arginine. Okay. And then the L-arginine is going to either be utilized for amino acids, or it's going to be, it's going to end up producing a byproduct of urea. And then you're going to end up producing the amino acid ornithine. Ornithine is, it's just it's going to be like a transfer amino acids to sit there, and that's going to be involved in the production of the citrulline. Okay. And citrulline and ornithine are not utilized, are not amino acids that are utilized in the in proteins. They're just utilized in this process, okay, in the urea cycle, and that's it. So they kind of, well, this cycle, and they're also utilized in another cycle for the production of nucleotides or nucleotide formation. So they act as carriers, okay? Okay, so to kind of get energy from amino acids are going to actually have to be broken down. And remember where we just talked about the ammonium ion formation? So that ammonium is going to be coming from that, the breaking down of the particular amino acids as needed. And so our preferred choice of food, if we're a cell, is going to be what? What is going to be a preferred choice?
For energy, sweet. Sometimes it's sweet.
It's sweet. So it's going to be that glucose. That's going to be our preferred choice, right? And then everything else is going to, I mean, although we need all of those components because we need to kind of recycle all those components, let me clarify. But our preferred choice, the easiest way are the sweets, right? And then the proteins and stuff, if we're not getting them from outside sources, we're going to have to utilize them from our own body. So we're going to have to cannibalize our body. Okay. So sweets are the easiest ones to process. They give us a lot of energy, a lot more energy typically than the proteins do. Proteins, they're more sustainable energy because it takes a while to get the process. We don't feel the effects as fast with the protein that we do with the sweets, right? So like if we get a sugar high, we crash a lot faster because we process it a lot faster. It's easier to process. Does that make sense?
Yes.
Where if we have we eat turkey leg and, ham hocks, and maybe not ham hocks.
Something heavy, like roast beef, and you feel all tired.
Yeah. So those things sustain us because it takes a while for it to get totally processed to be utilized for food. Okay, so here, this is basically this is where the sugar is going to be entering, right? So we have glycolysis that break it down into sugar. This is the point where the amino acids are also going to be coming in at that point of the pyruvate molecule being formed. And then you're going to get this acetyl-CoA, and it's going to enter in the cycle that way. So you have the gluconeogenic amino acids, meaning that they have aspects of sugars that can be easily processed to be sugars. Those are going to be alanine, cysteine, glycine, serine, and threonine. And you guys remember that there are 20 amino acids that are used in the makeup of proteins, right? And so that's 5 of the 20, right? Okay. The ketogenic, right? So those are the ones that are going to be kind of like those fats that we had, right? And so we're going to be burning that fat, okay? So these guys are going to have long carbon chains. They're going to be hydrophobic, okay? So these guys, that's alanine, that's going to be tyrosine, that's leucine, that's glycine, tryptophan, that's isoleucine. So then that's another 6, right? So those guys are going to be entering at the level of the acetyl-CoA. So and that's going to be done by the keose oxidation. And so very similar to fats, this is the point where a lot of our fatty acids and stuff are going to be entering that cycle. Okay, so as we go through the cycle, so this is the Krebs cycle down here. So we have arginine, histidine, glutamine, proline, and glutamate. These guys, they're going to be kind of similar to our alpha ketoglutarate. So because of that, they're going to enter at this part of the Krebs cycle. Isoleucine, methionine, valine, these guys are going to be kind of similar to succinate. So they're going to be entering at that part of the cycle. Okay, so then that's 3. And then we have our phenylalanine, our tyrosine, which we've already talked about phenylalanine. they can also be used to enter at this component of the cycle. And then lastly, we have aspartic acid or our aspartate and our the asparagine. Let's see, asparagine. Asparagine. Sorry, asparagine. And think about the term there. So we have aspartic acid and asparagine. They're going to be in at the point where we have oxalate. Okay. Are you with me so far?
Yes.
What was I going to say? Okay, so then that's going to be the last ones. Okay, so that should be, make sure we're adding right. So that's 11, that's 16, that's 19, and then 18, 20. Correct. Did I miss out? Isoleucine, so 2 here. Okay. Okay, so that should be all 20. So we have, you can enter at the late stages of glycolysis, right? If you're gluconogenic amino acids, or you could enter at keosis oxidation if you're ketogenic amino acids, or you can enter within the Krebs cycle if you're the others, right? And then some of them that fall in the category can enter at multiple sites. Okay, so this here is just a combination of the entire metabolic pathway. So that's the metabolic and the anabolic pathways combined. Okay, the catabolic is going to be the one in blue. The anabolic is going to be the one in green. Okay. Okay, so at this point, we've kind of talked about each of these different pathways, and so you should kind of be kind of familiar with it, pretty much. And actually, let me go back. So this should be ketone, not ketose. Okay. So let's see. Overall, we have overall we're going to have the entry of your amino acids. This is going to be the entry of your sugars, so your saccharides. This here is going to be the entry of your lipids. You're also going to have, although it's not showing it here, you're also going to have lipids that are going to be entering through this process as well too. My line here. Let me correct that. No lipids production. So your ketones are typically a sign of breaking down your amino acids first. And so if we think about weight loss, we typically get ketones broken down first so we get our ketone oxidation happening before we get our lipid lysis or beta oxidation. Okay, so have you guys heard of it's the keto diet? It's also the Atkins. Atkins was the one I could remember last time. You've heard of the Atkins diet?
No.
No. Okay, you've heard of the keto diet, right?
Yes.
Okay, so in the case of the keto diet, what are you doing? What are you eating? So you're
More
substituting.
fat.
Are you eating fats? Or are you eating? It should be protein, really, because most of the things that you should be eating are protein.
It's protein.
Okay, so
No carbs.
we're breaking down. Basically, we're limiting. It's low carbs, right? Low carbs, high protein. So basically, you're limiting this process. You're not getting this process. Everything is going to be coming into this process, right? So you're just adding in here. So the sugars remember, the sugars are going to act faster. They're our primary source, what we typically like. It's really quick. It gets to our system fast. It goes through our system very fast. Where protein, we know that it sustains us, right? We eat a big, healthy, hearty meal of protein, right? Steak, eggs, we get that protein. Now, what happens is by us feeding into this pathway, we also are going to need a supplement, right? And so if you get the right amount, you're saying that, hey, you're telling your body, I'm breaking down protein, right? So I'm cannibalizing, because it's thinking, you're cannibalizing yourself, right? So you're cannibalizing yourself. So it's going to get into your fat storage. Okay, so then it's going to start breaking down your fat. So then you're going to get this process happening. So you're going to get triglycerides and then so on and so forth, right? So you're going to get the formation of that. So your fat storage are going to be pumping into this pathway at this point. So you're kind of tricking it. You're tricking your body in a sense to say, hey, I'm eating my protein. I'm eating up my muscle. At the same time, your body says, okay, we've gone through our muscle. We only have so much muscle. If we eat too much, we won't be able to do anything. So let's start utilizing those fat storage. Okay, so in the case of the ketone diet, typically you'll take p-test to look at how much ketones are in your urine, because then that'll let you know how well you're processing and that you will be processing fat later on. Okay. Does that help?
Yes.
Okay. Okay. So absorptions. So our body has to go through and absorb things, right? And so there are going to be those key components, and we're kind of tying in everything. Kind of notice we're tying in all of the different aspects of different cells and different tissues and different organs that are involved in this process, right? So to break it down, so these are some of the signals, okay? So if you look up here, the red, purple, that should be a purple circle. The purple circle represents insulin. Insulin, we know what? What is the job of insulin?
I'm sorry. The job for what?
Insulin. Insulin.
Oh, to process sugar or break down sugar.
It is it's in the process of regulating, right? Okay, so it doesn't break down sugar. It's just lets our body know that we need to regulate it, right? So it's that hormone that is sent out.
Okay.
Yeah. So we know that it's involved in sugar regulation. Okay. So if we digest, so in step one at the top, we're going to be eating stuff, right? So we're going to eat it. We're digesting. Okay. So we digest it. It's going to enter the bloodstream from the intestines, and then our blood sugar is going to basically rise. So if our blood sugar rises, then the pancreas is going to be secreting insulin. So it's going to let us know, hey, blood sugar is rising. Okay, so then that sends a signal out. And then we're going to start, as a result of that signal, that insulin being released from the pancreas. The insulin is going to cause the cells to start taking up glucose, right? Because we want to kind of clear it out of the bloodstream and everything like that to try to get back to our normal state, which is kind of letting the body know that, hey, you ate something, food's here, it's time to grow, right? Liver cells, so they're going to be absorbing all of the excess glucose, and they're going to be converting that into, into glycogen that is going to be used for storage for later on. So we're going to basically go from those individual sugar molecules, we're going to just package it up and store it nicely. Okay. And then they're going to get to a point where you've kind of, generated a lot of that storage, right? And then we've gotten those storage maxed out. Okay. So then your blood, they're going to be actually also doing a little bit of storage, but primarily they're going to be utilizing, they're going to be kind of lean and everything like that. So your blood cells are going to be sitting there utilizing a lot of it, but your muscle cells are also going to take some of those glucose molecules, and then they're going to store those as glycogen molecules, right? Okay, and your amino acids, they're going to be actually utilized for the making of more muscle cells, right? So you're going to get more protein, not muscle cells, but more protein. So you're going to get more synthesis of actin and myosin, and kind of build up those muscle fibers. In the liver, the amino acids, they're going to be converted to ketone bodies, and then they're going to later be converted to acetyl-CoA. And in the case of your fat cells are going to take that excess glucose, and then it's going to actually start utilize it to make more lipid structures. So your fat, your lipids, and it's going to use the fats that are also being generated in there, and it's going to cause the fat to also be stored in your adipose tissue. So if you think about it, your adipose tissue is going to be the primary source of, majority of it is going to be lipids, right? Which makes sense. That's our fat cells. That's where I get my love handles and stuff like that, right? We have our muscle. That's going to be kind of like the storage of our amino acids and a little bit of our glycogen. And then the liver is going to be our primary storage of glycogen. Okay. Good so far?
Yes.
So that happens during absorption. And after absorption, post-absorption, right? Post-absorption, basically that means that we don't have any nutrients, right? In our bloodstream. And so as a result of that, we have a low blood sugar. We have no blood sugar around, and so you're starting to get a little hungry. So what happens is your pancreas secretes glucagon. So glucagon just tells us, hey, you have a very low blood sugar. We need to start producing some sugar to put into the bloodstream. Okay, so when that happens, the glucagon is going to go to the liver cell. Low blood sugar, we need to start making some more glucose, right? So it's going to go to glucogenolysis, where we're going to basically take glycogen lysis. It's going to take glycogen and break it down to glucose molecules so that we can start getting more glucose being generated. And it also is going to go through ketone oxidation so that we can sit there and make a little more ATP and also make a little more glucose from the amino acids. And then the muscle is going to start also go through the glycogenolysis and break down the glycogen that is stored in the muscle cells. And then, if necessary, they'll start cannibalizing the muscle protein, and so that you'll get catabolism. Oh, I just thought about that, cannibal catabolism. I never put that together before. Okay, so in that case, you're going ketone oxidation. Which is actually going to be happening in the liver. But it's going to allow muscle proteins to basically produce ATP, and that's going to undergo ketogenesis and ketone oxidation. And then in the case of the adipose tissue, so in the adipose tissue, you're basically going to release some of that stored fat, and then it's going to release fat molecules, and those fat molecules are then going to be broken down to make more glucose and ketone bodies and ATP. Or I should say lipid molecules to be precise. Okay? Questions? Concerns? Cash? So literally what happens in the case of the muscle cell will actually export your actin and myosin molecules. Sometimes it's peptides or polypeptides, long polypeptide chains, and sometimes full protein. So, okay. So the regulation of temperature. So we need that heat balance, right? That energy and heat balance. So the way that we do that is the hypothalamus actually controls that regulation component of it. And this is the diagram. We kind of showed this diagram before, but not as much detail at the very beginning of the semester. So in the case of our body temperature under cold weather, our body temperature is going to get low. So in the case of our body temperature getting low, we're going to have our temperature receptors in the hypothalamus be stimulated, and then we're going to be producing, it's going to start us producing heat. Okay, so it's going to send those signals. So the first thing that happens is that you're going to have your superficial arteries are going to constrict, and as they constrict, you can't see it here. Let me see if I can trace it to a better view. As they constrict, what's going to happen? You're going to get flow closer internally, right? So, and as a result of that constriction, you're going to have less heat loss of the blood, because you're going to limit the flow to the upper layer, and then you're going to increase the flow down here. So because you're constricting, it's going to kind of cause you to continue the flow. Over time, that blood flow to your digestive system is going to actually decrease, right? So when it's cold, under cold temperature, you're going to have less blood flow to your digestive system. So you're also going to get shivering. You're going to start shivering. It's going to basically, by you shivering, is going to increase the anaerobic respiration in the muscles, and then that's going to cause anaerobic respiration. Basically, is going to cause the generation of ATP. It's also going to result in the release of heat. So a shivering causes heat generating for us, and then the thymus is going to stimulate cells to increase the metabolic heat effect. So it's going to sit there and tell all of the other cells, hey, we need a little more temperature. So we need you guys to start burning some of that ATP that we have stored, or start making more ATP so that we can make more heat for our system. Okay, so then our body temperature increases, and then we go through that process all over again. So in the case of on hot days, what will happen is that our body temperature is going to be hot. Our temperature receptors are going to be initiated, and then they're going to go through that heat releasing mechanism. So they're going to send a signal, hey, it's way too hot here. We need to sit there and start turning on these things that are going to cool us off. So in this case, our superficial arteries are going to dilate. They're going to cause flushing. So you're going to get a fast increase of blood to sit there and try to cool off that system, right? So blood flow that would normally be that was diverted away from the digestive system is now going to be flowing within that system as well. So as a result of that, we're going to start sweating, and so we're going to send signals to those glands to sit there and start secreting. They start sweating a little bit more. Then the thyroid is going to stimulate cells to decrease the metabolic heat. Okay. So in that case, you're going to say, well, okay, we don't need to be making all that ATP, because every time that we make that ATP, we're also making heat that goes on with that, right? So you guys both should appreciate this, since you guys both were in my chemistry class. So C6H12O6 plus O2. This guy, just in general, this guy is what type of reaction in terms of chemistry? You guys remember? It's called a what type of reaction? Actually, all three of you guys, since you have my chemistry class. We talked about this a whole lot. What happens if you take a piece of wood and you're out in oxygen and the wood catches on fire?
Gasoline. I mean,
It happens with gasoline too, but
yeah, I just remember. It's just I had it in my mind, but I know what I know what you're going into. It's just
what type of reaction? Starts with the C. Burn, baby, burn. Combustion. That's right. It's a combustion reaction. Okay. You should know that, Leticia. It's coming up real soon there. So we have a combustion reaction, right? So literally, this here is glucose. This is also cellular respiration. Okay, so we're basically causing heat to be generated. So the products of this is going to be ATP and heat. So you're telling the body, you're like, hey, in the case of it's being cold, it's cold, man. It's really cold. Your body sends the hypothalamus, sends signals to the hypothalamus. The hypothalamus gets stimulated to say, hey, we need to produce more heat. Where do you think you're going to get the heat from?
from the glands?
Well, the glands are going to be used to kind of help regulate the heat. So it's going to either be cooling off or adding it up. So your heat is actually going to be coming from your cellular respiration. You're going to kick in that cellular respiration, so you're making more and more heat, right? So you're going to use a lot of your stored. Why do you think bears hibernate in the winter?
To keep warm?
Sort of to keep warm. So what happens right before they get ready to hibernate? They pack on the weight, right?
Mm-hmm.
They're not out searching for food in the winter. They're sleeping. They're like, I'm going to sleep. Part of that is to keep warm. They put on a lot of weight, a whole lot of weight. The reason why they pack on so much weight, they get fat right before, because they're going to be utilizing all of those resources, all of those reserves to sit there and make ATP to stay warm in the winter. Okay, so that cellular respiration is going to be utilized to sit there and make that heat. Okay, so we're going to be generating heat. We're going to be using cellular respiration for that process. So it's really important that we do that constriction, because we want that blood flow, but we want that blood flow to be closer towards all of those inner organs that need all of that ATP to kind of keep functioning. And you want them to keep functioning because they're making heat. They're utilizing that energy, right? They're going to be pushing it in that path. Does that make sense?
Yes.
Okay.
Yes.
So muscles are shivering, right? So if muscles are shivering, aren't they going to be utilizing this process? Breaking down some of that glycogen, making, you know?
Yes.
Okay. Okay. So are you guys kind of seeing how it's all being tied together, that whole metabolic process and everything being tied together with the regulation in terms of temperature, in terms of calcium homeostasis, you know?
Yes.
Okay. So I think it changed quite a bit since I was a kid in terms of we used to call it the pyramid, the nutrition pyramid. Food metabolism plays a huge part in everything. And so I can't say what the numbers are today because I don't remember what they currently are, because like I said, when I was growing up, they were slightly different.
Yeah, they were.
Than what they are right now. But basically we know that we do need the fruit, we need the grains, we need the vegetables, the protein, and dairy. Dairy is kind of a form of protein, but it also provides other components. When we break it down, it breaks us down to all of the different components that we need for our body. We need the fiber for the cleansing component. We need which is also part of the saccharide, right? But we can't break those down, the fiber component. We need the saccharides, which are going to be our simple saccharides, our monosaccharides. It's also going to be our simple carbohydrates and our complex carbohydrates, saccharides. We need protein, right? And that's going to provide our amino acids. And we need our lipids. And so from all of these different foods, we sit there, we get a lot of those components, plus we get a lot of the minerals that we need as well too. And a lot of times in the right proportions if we eat appropriately. And so it's going to be crucial for that. And sometimes we'll need supplements that are going to be added on. A lot of times we get the vitamins from our fruits or vegetables, our grains. And then your book actually lists all of the different vitamins that are often used. They kind of break them up in terms of their solubility, and the solubility kind of helps us. partially some of their functions. So we have some that are going to be fat soluble and some that are going to be water soluble. And so you want to kind of pay attention to that. Like for instance, vitamin K is involved in clotting. So I have a deficiency in vitamin K, or in one of the factors that are responsible for vitamin K. So I have to take a vitamin K supplement. So I don't clot right in most cases. And so a lot of times we're going to need to supplement ourselves with those different vitamins. We also have major minerals. So that's going to be like calcium, potassium, magnesium, chloride. So those guys are going to be major. We kind of need those electrolytes in our body to kind of keep that electric potential happening in terms of the neurons and keeping those neurons firing. We also have trace minerals. That's going to be like our zinc, our cobalt, our selenium. Most of them are going to be like those metals, right? Those heavier metals. We're going to need small amounts of those, and that's hence why we call them trace. Okay, and so all of those play a key role in metabolism. And if we're short on them, then it causes issues. Like for instance, if you're short on iron, it causes anemia, weakness, fatigue. So do you guys ever have moments where you're craving red meat? God, I need a burger. I really need a burger.
No,
You never have that?
no, it's mostly ice.
You said ice?
Yeah.
So then you have no lack of water, so you need water.
Usually it's the cold things.
What was that?
I see. Usually
said-
it's dementia or cold things or sweet things at the same time. I don't know.
So you have a craving for sweet things. Is that what you're saying?
Yeah, and then something's for souring things.
Sweet and sour things. Huh. So sour things are typically your pH balance is typically off. So if you're having a craving for sour things, you're trying to get that H plus ion in you. So that's what you're typically trying to get. Sweet things typically means well, I have a craving for sweet things. Typically, sweet things could be a combination of two things. One thing, it's you're trying to get glucose in you so that you, and glucose fast, because either A, you're dehydrated, you're not producing enough water, or you don't have enough water in you, so you're trying to use the food to produce the water. That typically happens to me as a result of fudginess, right? Or you're just not getting enough nutrients in general, and so you need to add on a little more eating. And since sugar is the quickest form and easiest to process, your body is craving sugar because it's like, hey, I'm a little hungry now. We need something quick. Okay. So let me pull up your next slides. How are we doing on time? We got 30 minutes. Okay, you guys realize that this is the last lecture. So we're going to cover what we can cover. And then anything that's left over, it's just going to be left over. I'll give you guys slides so that you guys can take a look at them on your own. But everything is in the book. So if you read the book, you'll be good. One second. Okay, let's see. Okay, so the next thing that I'm going to talk about is the urine, the urinary system. You know, you can never avoid talking about pee. All right. Okay, so this is a, can you guys, yeah. So this is a salvage treatment plant. And so a lot of our waste essentially goes through that process. So like the salvage treatment plant, there's a process where everything, all of our waste typically go. Same thing happens to us. We actually have a whole system to kind of get rid of waste, right? And that involves the release of water, right? And so we talked about water absorption and reabsorption, right, earlier, and that process and how much we need to take in and how much we're actually releasing and all of that. And so here we're going to actually talk about some of that release, that release of some of that waste. Okay, so this is a color of urine. So we know that our body needs water. Our body needs water for tons and tons of processes. One of the major processes that our body needs water for is hydrolysis. Hydrolysis is used for metabolism or anabolism. Which one? Metabolism is what? Is that breaking or building?
Breaking.
Breaking. Okay. So catabolism is the breaking down, right? So hydrolysis, lysis basically means breaking down. So you're using water to break things down. So although it's used in both processes because there are points where you're going to have to use water to break one component to make another component, right? So it's used in both of the processes, but it's primarily heavily used in metabolism. So we need to stay hydrated. If we're not hydrated, we're not getting enough water in us, and then we're actually we're putting out things that we may need as well too, which is going to end up causing problems, right? Or we're not breaking down things the way that should be broken down, so they're not they're only partially done. So this here, basically when our pee is light in color, right, it is hydrated. So often we'll use the urinary system to sit there and let us know how we're doing in terms of our hydration. We'll also know if there are any type of internal issues, because if our pee is slightly red, what does that tell us?
Well, something is wrong.
Something's wrong, right? You have some type of internal damage that's causing bleeding, right? If our pee, if you take a look at as it gets darker in color, that means we're dehydrated. Okay. So we know where pee essentially comes from for both of us, or urine comes from in both of our cases. So the urethra is responsible for transporting urine from the bladder to outside of the body, right? And this is basically an image of both the male and the female urethra. We won't go into the anatomy components of it. So the way it basically works is that blood flow is going to be flowing through the kidney. The kidney is going to be responsible for doing all the cleaning up. So it's going to be like that filter. Some of the things are going to be reabsorbed, reused, and some of them are going to be sent out as waste. Okay. So let me go back one step. I also want to add Urine, if it's okay, it should be almost odorless, right? It's going to have a little bit of odor as it sits because it's getting more concentrated and things are being broken down the way it is. But if there's something wrong, it typically lets you know that by the smell that there's something wrong, or by the color. Okay, so typically urine can be from a pH of 4.5 to 8. It's going to have various physical characteristics that are going to be pretty consistent in a normal individual. Okay, so if you start exceeding those points, then you're out of that range of normality. There's probably something wrong. So if your pH, if your urine is very acidic, you know that there are issues that are going on. Probably since it's acidic, it has something to do with that's going to be involving those protein channels, or the proton channels, not protein channels, or the protein pumps. And if it's basic, that could also be a result of you maybe secreting too much bicarbonate or something along those lines during your digestive system as well. So we want to pay attention to that. Also, the volume of urine, right? So normally you should pee about 1 to 2 liters a day. Above that, there's typically something wrong. If you're peeing more frequently, if you get to greater than 2.5 liters a day, that's typically a sign of diabetes. Or too much caffeine, too much coffee, you broke the seal. So anything that's basically a diuretic. It can also be a result of sickle cell anemia, excess water intake. You're drinking way too much than what you're supposed to. If you're urinating too little, then your body's dehydrated. Either that, you lost blood, diarrhea, you're having a cardiogenic shock, kidney disease. You may have a inflamed or an enlarged prostate. And then if you're urinating very little to not urinating at all, that is a huge problem. That means you have kidney failure, or you have obstruction, a kidney stone, or a tumor, or your prostate has gotten so big that you're not able to urinate. Okay. Good so far?
Yes.
Yes.
Okay, so back to that flow. So so the job of the kidney is going to be kind of like a filter, or it's going to be responsible for cleaning up the blood. So, excuse me. So, okay, so in the kidney, I should say, first off in the liver, we have the release of various enzymes. Okay, so the liver's basically going to release the angiotensinogen into the blood. So then you're going to have the angiotensinogen is going to then be converted into angiotensin 1, and that's going to be done by the renin enzyme. And this guy is called a pre enzyme. So it's not, I'm sorry, it's called a proenzyme. So it's not completely functional. It has some functionality to it. It will act on certain things. It has its own thing that it's responsible for, but it's going to be further activated. So then it's going to be converted from a proenzyme where it's not completely activated. It has limited processing powers, right? So that enzyme then is going to be further processed to the active form, which is the angiotensin 2. And that's going to be done by the ACE enzyme, which A stands for the angiotensin converting enzyme. So it's going to convert it from that the poorly to no active form of angiotensin 1 to the active form of angiotensin. And so this process is happening as a result of a couple of different organs, right? The liver is going to be releasing the pre-pro form. The pro form, you're going to get pulmonary, it's going to be a result of your lungs and everything that are going to be secreting another enzyme that's going to respond for the further activation of that. And then this form here, it's actually going to be functioning more so in the kidney, right? So then what happens is that the angiotensin 2, it's actually going to stimulate, the release of steroid hormones, the steroid hormones, aldosterone, and then aldosterone is going to, or I should say, it's going to stimulate the adrenal cortex to release aldosterone. And then aldosterone is going to be responsible for the sodium uptake by your apical cells, your apical cell membrane. So you're going to get that gradient forming. And so as a result of that, right, that could actually lead to an increase in our blood pressure. Okay. And then also further lead to water retention, or water retention, sorry. Okay, and in the case of the reason how it ends up leading to water retention is because it causes the water channel to sit there and open up as well. So as you are getting the positive charge, it causes the pore to open up. So that change in gradient that we saw with the sodium ion causes the pore to open up, and so then water is able to sit there and move through the channel. Okay. So okay, so if we look at the net filtration pressure, so in this case, we're going to be looking at the sum of the osmotic and the hydrostatic pressure. So here, this here represents, in one case, it represents the blood hydrostatic pressure. It going into our or valve here. And then we have the colloid osmotic pressure going in the other direction. And then we also have the capillary hydrostatic pressure going in. So we have two cases where we have the blood going in, and we have one cases where the blood is going out. And so overall, you're going to get a balance that is occurring. Okay, and so when the kidneys is going through that process of that filtration event, you're going to have both of those playing a part. Things are going to be going in as things are going to be going out. Okay. Okay. Okay, so you're going to have tubular reabsorption and of various components. Components that are going to be found in your bloodstream that are going to be flowing through as you're doing that filtration. And so that's going to actually be reabsorbed in the kidney itself, in the tubular component of your kidney. And so basically your nephrons of the kidney are going to be responsible for this process. So you can kind of see here on the earlier stages of your nephrons, you're basically going to get absorption of glucose, amino acids, proteins, vitamins, lactates, urea, uric acid, tons of different ions and water. Okay. As we move further down the process, we're going to get urea, uric acid, creatine, and then other drugs that are going to be absorbed. As we continue down further, we're going to get more water, your ions, and that should be a sodium plus, not a sodium minus. And then we're going to get further discrimination. That's going to be happening as we move further and further down. So it's going to get more purified towards the end. And then you're going to end up with a clean product at the end of the day. Okay. So as we complete our travels through it. Okay. So I should say, these guys are going to be absorbed. These guys are going to be secreted. These guys, water is going to be absorbed. Urea is going to be secreted. And so that process is going to be that moving and taking at various stages of secretion and absorption of the components. Okay. Questions, concerns? Cash?
Nope.
Okay. Okay, so this is just kind of giving you an idea of how substances are going to be reabsorbed and secreted. Okay, so this here is going to be the lumen of the proximal tubule. This is going to be the proxial tubule cell. So as you take a look here, you're going to have your hydrogen ion is going to be transported to the proxial tubule, lumen of the proxial tubule, where the sodium ion is going to be going the counter direction towards the tubule cell, and so that's going to be a coupling channel, and so one is going to flow in one direction, one is going to be flowing in the other direction. And so same thing is going to be happening with other channels where you're going to have the sodium or the sodium ion, again, flowing in one direction, but you're also going to have the chlorine ion flowing in that same direction. It's going to be coupled with that proton channel. And so on and so forth as we move down. And so it's always going to be a coupling event that's going to be happening. And as a result of that, you're going to end up getting sodium that is going to be secreted into that intermolecular space, and then that's going to be put into the bloodstream. So you're going to end up with sodium in the bloodstream, we're going to end up with calcium in the bloodstream, or you're going to end up with amino acids in the bloodstream or glucose in the bloodstream. Okay? Are you good so far?
Yes.
Okay, so after you've reabsorbed all of that stuff, you're going to be putting some of that back into the bloodstream so it can be reutilized. Okay, so you have this nice system of absorbing and secreting to kind of keep some of those nutrients, make sure those nutrients are being utilized effectively. Okay, and the ions are being utilized effectively. Okay. And then, of course, we know that this channel, this processing, the secretion and the intake, the absorption, we know that that is often coupled with energy. You need energy to make it happen. So those channels don't open unless we have energy present. So it has to be facilitated, or what we call active transport. Okay. So this is just basically looking at the reabsorption of biocarbonate. So we often will use biocarbonate to kind of neutralize the acids in our stomach, so they don't destroy the wall of the intestines and things like that. So we know that the pancreas is responsible for the secretion of that. And so that we recycle it, it also has to be reabsorbed again. Okay, so in that case, that's what's going to be happening here. So in the lumen of the proxial tubule, it's going to be responsible for that, the absorption, and so of the biocarbonate. So we're going to get the biocarbonate, and then we're going to utilize the proton, the hydrogen ion, and we're going to make carbonic acid. So then that carbonic acid is going to be processed to water and carbon dioxide. You may not remember, oh, we didn't do it in your class as a center, but we did it in your class, where we actually we used baking soda with acetic acid, or with vinegar.
Yes.
You remember that? And then we end up making carbon dioxide, the balloon blew up, and water.
Yes.
So this process, that's essentially what you're doing. So you're taking the hydrogen ion from, in the case of vinegar, an acid, that H+, you're making carbonic acid. Carbonic acid is broken down, although this is happening so fast in our body that we use an enzyme to sit there and make it faster. It happened pretty fast because of the reaction, but we need it faster in our body. So we use this enzyme to make it happen faster. We break it down to water and carbon dioxide. So then the water and carbon dioxide are able to sit there and go through into the cells. So it can be absorbed in the cells. And then go through that process, this is the first of it. You're making that carbonic acid, then you're getting that proton, and then you're getting your carbonate, your bicarbonate being reproduced, and then it's going to be exported with that sodium. Okay, so then, in other words, we're going to have this nice cycle of that regeneration, but you're using the fact that you're making it and unmaking it to sit there and allow it to pass through, right? So the carbonate itself wasn't able to get through the membrane at this point. There's no channel to sit there and do it. So it makes that carbon dioxide allow it to get through the membrane, because we know that carbon dioxide is a non-polar molecule. So it's going to interact nicely with the lipid structures and things like that. And we're able to sit there and get it to pass through, diffuse through that membrane, and then it's going to remake the bicarbonate, and then we can recycle that and then allow for it to be released back into the bloodstream. So, okay.
Okay.
So the kidney, if you think about it, is serving a couple of functions, right? So it cleans things out, but it also makes sure that things that we're going to need, we're recycling. It goes through that recycling component. We recycle that bicarbonate. We're recycling the glucose that wasn't fully processed. So you're not wasting too much. So again, if we take a look at our urine, if our urine is giving us a lot of glucose, that means that there's something going on. That probably means that there's something wrong with our kidney, because then our kidney is not filtering out those things that we may need. If we're losing a lot of amino acids, it lets us know that something is wrong with our kidneys, right? So that's going to be the first thing. So often we would use the urine as means of testing whether or not something is going on in our body. By doing that, by looking at what are the things that are being released from our body, we can have a good idea of where to start looking, right? If we're getting everything being released, right, then we know, let's say we have high sugar being released, we know that we're getting a lot of amino acids being released, we're getting sodium bicarbonate being released, then we know that our kidney is not fine. It's the kidney that's screwing up. If we're getting one of the specific components, then that can kind of let us know, okay, it might be, hey, maybe the liver, if we're getting a lot of sugar released, right? Or it may be muscles, if we're getting a lot of amino acids being released. Do you understand?
Yes.
Okay.
Yes.
So we can use the physiology of things and the fact that we know where things are going to be stored at, what's going on. If we're getting a lot of fat being released in our urine, what is that going to tell us?
That we may need to lose some weight.
You may need to lose some weight, okay? Or our adipose tissue, something is going on with our adipose tissue. Or maybe it's not the adipose tissue, maybe it's the liver, because the liver is responsible for doing lipolysis. And so it can kind of lead back to that. So then you'd want to look at other markers. So does it make sense how we utilize what's supposed to be normal and how that fluctuation can tell us, hey, these are some of the things that could be going on? Yeah, no, maybe? Can we just keep going?
Yes.
Okay. Okay, so this here is just kind of giving you the fact that you have that counter current going through the nephrons of your kidney, and so you have the water going in one direction, you have the urea going in the other, and so you're constantly having that happen through this process. And so water is being reabsorbed and the urea is being pushed out, right? And so as we go on, you're using some of that later on, so that water just sit there and help with the recovery of the ion, right? Okay, so are you guys good with that? You kind of see how that works?
Yeah.
Yes.
Okay, so in terms of the regulation, so we have to regulate blood flow in the kidneys because too much can cause issues, too little causes issues, right? And the way that they're regulated, it's going to be regulated by your hormones, right? So your your so your growth factor, or your G, your your growth factor release hormone, your GFR. Sorry, no, your okay. So your GRF, your GFR, which is um, your glomian it's the filtration rate, the glomi ruler filtration rate, and then you have your renal blood flow. So various hormones are going to be responsible for kind of regulating that process. Okay. If you have, in one case, you're going to have vasoconstrictors, so hormones that are going to be responsible for affecting the sympathetic nerve system. So like your epinephrine, your adrenaline, that's going to end up causing a decrease in extracellular fluid volume. And then that's also going to affect your GFR, and it's also going to affect your renal blood flow, your RBF. It's going to decrease it. Angiotensin 2, again, will cause a decrease in your EF, your extracellular fluid volume, decrease in your GBR, and then also your RBF. And then endothelin also causes the same thing, but you're going to end up with an increase in stretch. You're going to increase your angiotensin 2, and you're going to increase your epinephrine. So, and then that's just going to cause, as a result of that, it's going to end up causing your ECF to decrease, and then your GFR to decrease, and so on. Your prostaglandins causes your ECF to decrease, but you end up causing more stress, more shear stress being generated, and you cause an increase in your angiotensin 2. But because of that shear stress, you're going to get a result of an increase in your renal blood flow, and you're going to get an increase to no change in your GFR. So where nitric oxide causes an increase in shear stress, and that's going to end up causing both of them to go up. You're also going to get an increase in your histamines, ATP, and adenosine. Other components go up too, but they have little to effect on it, but you're going to get the stimulation of that. Bradykinin is going to cause your ACE to go down. It's going to cause your prostaglandins to go down. I hear me on repeat now. Okay, and then we have the natriuretic peptides. Those guys are going to cause an increase in your ECF V, and it's going to cause an increase in your GFR, but it isn't going to have an effect on your RBF. Okay, so basically, if we look at this, some of the enzymes are going to be responsible for your dilation, and other ones are going to be responsible for your constriction. And as we see the endo, so these guys, like indolent, so in a normal person, a normal individual, a normal healthy individual, it's not going to have an effect on their blood pressure normally in a healthy person, but in a case of a person that has like that's diabetic or something like that, it's going to end up causing sodium retention. And so you're going to end up getting sodium retained in that system, and that is going to end up causing elevation of an individual's blood pressure. But under a healthy individual, it's not going to have an effect at all. Are you good with that?
Yes.
Okay. Where? So if we have the case of the natriuretic hormones, so these guys, they're basically going to be peptides. They're going to stimulate the kidneys to secrete sodium. And the way that their process is that these guys actually inhibit aldosterone from being released. And then as a result of that, that's going to inhibit the sodium recovery system. Okay, so then you're not going to recover so much. Okay, so it's thought that these guys are kind of responsible for like fine tuning the blood pressure in terms of the regulation of the blood pressure. So you guys kind of understand how that whole concept of sodium is going to be playing a part in terms of your blood pressure and everything?
Yes. Too much of it will increase the blood pressure.
Okay. So these are some of the nitrogen waste molecules. So we're going to have aluminum, urea, and uric acid. You kind of see the blue represents the nitrogen, white versus hydrogen. That's oxygen. So these are the chemical models for each of the compounds. Let's see. So we had talked about this earlier, where we're getting the conservation of we're getting conservation. I mean, not conservation. We're getting the conversion of the angiotensin to angiotensin 1, and then also angiotensin 2. So the kidney is responsible for actually releasing the renal enzyme. So that is responsible for the clipping of that. And so you can kind of see this loop, this regulation, this feedback loop, where the liver is responsible for the generation of this, the kidney is responsible for this, and this guy has an effect on the nephrons in the kidney. And so it's kind of like you have this negative feedback loop. So the processed enzyme, the active enzyme, lets us know that, hey, we need to shut this guy off. So we stop making this much, and then we stop secreting that guy out. So we have another negative feedback loop. Does that make sense?
Yes.
Okay. And so, but not only that, you also, like, the homeostasis is kind of complicated because you have a various triggers in the kidney, right? So vitamin D synthesis, erythropopsis. So erythropopsis is basically it's the production of red blood cells, high production of red blood cells, and then in terms of your sodium, that sodium regulation, that is going to end up affecting your osmosis. So all of those are key components that are going to be responsible for the regulation of the kidney itself. And then you also have this enzyme that's kind of directly responsible for that process as well. So often, we sit there, we think about it, right? Think about blood pressure. And what do you guys typically associate with blood pressure?
I think there's different factors. So some people get headaches.
Yeah.
Other people, I mean, when I'm really, really mad and I know my head blood pressure, like I can feel my veins warm.
Yeah.
And sometimes they hyperventilate.
Okay. So those are all like symptoms of blood pressure. So if we think about what are the things, so we know that like sodium, the sodium ion affects blood pressure. That's one thing that affects it. What are other things that affect blood pressure? Why is your head hurting when your blood pressure's up?
You're probably stressed, or you probably like were frightened. It depends, I guess, because some people get really high blood pressure from being scared, from being excited. There's a lot.
Okay. So you're saying that you just told me that the sympathetic nervous system feeds into our blood pressure. Is that what you're telling me?
Yes.
Okay. Okay, so that would explain. What about cardiovascular? Does the cardiovascular has anything to do with our blood pressure or anything like that?
Well, if we have issues with our heart, yes, as well.
So the cardiovascular system has issues to do with our blood pressure. And we know that we just talked about how the renal system has issues to do with our blood pressure as well too, right?
Yeah.
So basically, because all of these systems are kind of tied in together, we have to have signals. There are signals that are letting us know kind of what is the ultimate cause of that. And then that we're not really necessarily weeding it out, right? Because a lot of times, I know my grandmother, she takes 2 different types of blood pressure medicine, right? One is for one thing and one is for another thing. One has has an effect. It deals with the heart, cardiovascular component of it. And one of it actually she has an issue with kidney stones, and she just had a pacemaker. So, she has both factors going in there. So she has 2 different blood pressure medicines. One that's affecting her kidneys, one that's affecting her, or that's targeted towards components in the kidney, and one that's targeted towards components in the heart. So, okay, I think we're done, right?
Yes.
Okay, so your final exam is going to cover up to chapter 25, with various components missing because we didn't go over them directly. So the stuff that we didn't get a chance to cover, you guys are going to be responsible for on your own for future references. So just kind of keep the material, keep the book, don't toss it because you'll need it for studying for later on. When you take your nursing exam, T-stats, or you decide to go that route, what is it? T-test, the T's test, right? Or if you go to get your licensing for physical therapy, for those who are planning to go that route. Okay.
Okay.
Okay, so I will try to get that exam posted today. So you'll have until pretty much until final is due. You'll also have your final. So you have 2 exams. Both of them are just going to be multiple guess. So you guys do pretty well. You'll do the standard thing where you have your cheat sheet. I will put up a practice test. So I'll try to get that done as soon as possible. Okay.
Sounds good.
Okay. I'm gonna let you guys go. I will see you on. I'll see you guys. I guess I won't see you. I will see you next week. I will have a day next week where I'll come in and check them out. That's it. So no more lecture.
Will you let us know then? What
Yep.
day?
Yep,
Okay.
I'll give you the day so you guys can ask me any questions.
All right. Sounds good.
Okay, I'll talk to you later.
All right.
Bye-bye.
Have-